This is video number 1 for Computer Science 2124. Perhaps as is appropriate, since we've had such a long break, I'm going to start with the recall. Way back. Feels like months ago now. Recall the cat structures? Yes, the kitty cats back in example 10. They had information about a cat, and then each one pointed to the next one. So one cat was connected to the next cat, connected to the next cat. Same thing for the athletes. Remember them athletes? They were in program 5. Each one of those, actually both of those are special cases of what's generally known as a linked list, a standard data structure. And if you remember how those were dynamically allocated and arranged in memory, then linked list, I hope, is a pretty intuitive term. It just means that it's a list of things all strung together with one linked to the next one. It had a pointer to the next one. The full name of the linked list is a singly linked list, in our case, S-I-N-G-L-Y, linked list. But for us, it's just going to be a linked list, or maybe even just a list. The reason I put the full name singly linked list is that there are also circly linked lists and doubly linked lists and all sorts of variations. But we're going to look at just the generic basic version first, and maybe only, we'll see. The linked list, let me see. It's got stuff in a straight line, just like an array, and actually it's competing with arrays. I'll put linked list over here, and we'll do a tail of the tape. We'll do linked list versus arrays. In this corner, array, we've known those since we were programming infants. Arrays look like this. If I do a figure here, they have data like A, B, C, and indices like 0, 1, 2. And this whiteboard doesn't receive markers very well. I'm going to have to remember to try to keep it flat up against the board. Mental note. A linked list, if it's holding exactly the same data, would have A, but then instead of an index number, it has a pointer to the next node. I'll break the seal on that term. The next node in the list, which holds data B, and then a pointer to the next node in the list, which has data C. And by convention, remember, if we want to be safe, if C is the last thing in the list, we want to put a 0 there. So we can test that almost the way we'd test for a sentinel and see whether or not we've reached the end of the list. What is there for them to compete about? Well, arrays, we used those way back in the bounded buffer program, remember? So that one is bounded. If we're going to contrast, compare. Arrays are bounded, which means we start off with an upper limit of how many things can be stored there. Generally, we have to prepare for the worst case, which means if there could be 1,000 things in there, then we better declare our array, define our array with a dimension of 1,000, even though we might only use the first 7 or 8 elements. So it could be wasted space. Over here, theoretically at least, unless you run out of memory on your machine, a linked list, if you think about it, is unbounded. In the sense that since we are dynamically allocating nodes to put in our list a la carte, on demand, as soon as we need them, just in time, all the other cliches, then we're not taking up any more memory space except for that pointer in there. We're not taking up any more memory space than we absolutely have to. So we do not have to brace ourselves for a worst case over here. And let me see if the pink will write on the board. I'm going to award this round to linked lists. I make the claim that unbounded is an advantage over bounded. We don't have to know a lot of things in advance. We just deal with things as they come up. Arrays, however, have what's called direct access. And that sounds like that's a fancy term, but it's not. It means if you want element 1, then you go to index 1. If you want, maybe element 2, you go to index 2. You're going directly to it. You don't have to look at everything that comes before it. You can already predict what's coming over here, can't you? Sequential access. Remember, to get to the cat at the end of the line, we had to start with the first kitty cat and follow the next pointer, which I think was called BFF, if I recall. I'm surprised that I remember that. BFF to B, BFF to C. Oh, big deal. So we've got to step through some pointers to get there. Well, think about this. What if this is a large application and we've got 10,000 array elements? Doesn't really take any more time to get to element number 795 than it does to get to element 0. Direct access. Oh, but if we want to get to element number 795, whatever I said of our linked list, we've got to go through every single one. Because in general, we're only going to have a pointer to the very first one. My kitty, or the gold medalist, or whatever metaphor you want to fall back on here. We're only going to have a direct link to the very first thing in our list, and we've got to step through all the others. Thus, sequential access, and it looks like the second round goes to arrays. So far, they're tied. You know what? I just got this urge to say, does that make sense? Are there any questions? If there are, you better write them down, and we'll bring them up at the last class period of the week. What about over here, we want to insert something in order. Now, I didn't leave much wiggle room over here, but maybe we are inserting the letters in alphabetical order over here. And maybe we're in some really weird language where there's a new letter. Oh, I don't know, maybe it looks like a combination of an A and an E. I'll just make it up. A-E, and that should go in front. Well, I'm not going to mess up my picture because I'll have to keep redrawing it over and over. But if this is the first letter of this new strange alphabet, then that will have to go before A. Mentally picture this operation. We just put a new node over here and make our first pointer point to that, and make the AE pointer point to the old first one, A. A little bit of surgical maneuver over here at the very front of the list, and that's it. It doesn't even matter how many things are already in the list. We could have 27 letters in the alphabet, and we put AE, oh no, it needs to be the first one. Okay, we just insert it in front of the first one, and all the others are still in the right order. Contrast to, well, I'm going to say insert in order. That's easy. We can insert in order over here as well. Insert in order. I'm going to claim that, relatively speaking, if I can ever spell it, insert in order over here is hard. Hard meaning it is going to take a little more work to make this happen. Why so? Well, if we've got the new letter that we want to insert up front, AE, that front slot is taken by A, the old first letter. So what we have to do is start this domino chain reaction thing, copy C to the next element of the array, copy B where C used to be, copy A where B used to be, and voila, we've got space for AE. And again, you're ahead of me, I'm sure. What if we had 30 letters in there? Then every single one of those 30 letters is going to have to move down to make room for AE in slot 0. Which is not good. That's harder, I'm going to say, than all this little surgical operation over here. Now, we in the biz, if you've done some reading on your own, perhaps you haven't, if we were to look at the algorithm analysis of this, we would call this an order in operation, meaning the number of things that we have to do to complete that is directly proportional to how many things are already in the array. If we start with 6 things, we've got to move 6 things. If we start with 12 things, we've got to move 12 things. It's going to take twice as long if the data set doubles. This is called an order 1 operation because we can squeeze a new node between 2 nodes that are already in the list with exactly the same number of steps regardless of where we are in the list. So this round goes to the easy. And so far, it's 2-1. The linked list is beating out the array. What else we got here? The delete operation. I'll start with the linked list this time. Delete. Well, we've seen that. We haven't maybe done it in the middle of the list, but think about this. Mental experiment here. If we need to delete the B, for example, then what we do is we put our finger on that, maybe point a temporary pointer at it, bypass B by making the A node point past B on over to C, taking B out of the list. We've extracted it from the list. Now we can delete it. If we had a temp pointer pointing at B, then we just say delete temp. Let me see if I can walk through that and actually get the steps in order. We need to delete B. Oh no. Temp Set temp equal to the address of B. Set A's next pointer to the address of node C. Delete B. 3 steps. Not only 3 steps, it's 3 steps regardless of where we are in the list. I can delete B with exactly the same number of steps as I would delete E or F or G or any other node, as long as I have a pointer to that node. Guess what's going to happen over here? The delete, I'm going to say that's easy. Again, an order 1 operation, for those that are concerned about such things. What about the delete over here? Well, here comes that domino effect thing again. Suppose that we want to delete B. B is no longer an official letter of our alphabet. Off with you, B. So we delete B, but that's going to leave a gap here. If I delete B and B is gone, then I don't have a sequence that represents my alphabet or my set of strings or whatever it is that I've stored in the array. So here we go again. C would have to be copied over here to close up the gap that was left by B. Not only that, whoever follows C has got to be copied into C's place, and so on down the line, and that's what I've been calling the domino effect. We're going to have to do that over and over again. That's order N. That's hard. And it looks like linked list is zooming into the lead. Who needs your array anymore? So far, the only advantage it's got is direct access. But let's see. We'll toss it a bone. Give it an easy one. Softball. Overhead. OVER. Head. Per element. That says element. Overhead per element. In other words, is there some extra storage space attached with this to do accounting and keep up with where things are in memory and all that? No, these things are actually packed as tightly together in memory as they are on my whiteboard. So there is no overhead per element. No. Guess what's going to happen over here? Overhead per element. Yes. Now, a running theme, not just order of magnitude, how many steps is it going to take for this operation, yada, yada, yada. We've also got to keep our eye on memory. We don't want to be eating up a lot of additional memory that we don't have to. Where could that be a problem here? Well, suppose, just suppose with me, that these are not even really strings, they're not letters, they don't represent anything larger than themselves. They are actually characters in the ASCII character set in a computer. 8 bits, 8 bits, 8 bits. Big deal, that's not taking up a lot of space. I'm running it on my MacBook Pro, a 64-bit machine. 8 bits of data, 64 bits of pointer value. Yikes. 8 more bits of data, 64 bits of pointer value to point to the next one. Do you see what's going on here? 8 bits and 64 bits, 8 times 8 is 64. 8 times as much storage space is being used just to hold this thing together than is actually being used to store data. Yes, a clear victor in this. This one goes to arrays. Arrays win that. Less overhead per element. Now, a thing that I kind of slipped in without even realizing it at the beginning. How about this? Overhead. I hope you could read this font. If this isn't large enough and you need it larger so you can read it on your iPhone, then include that in your comments, okay? Overhead overall. Overhead overall means once I got all the data in there, how much as an entire data structure is wasted. Well, it could be a lot with the ABCs and so forth. So that's some overhead overall for the entire set of whatever I've stored in my data structure. What about overhead overall here? Well, you may think, well, they're packed so close together, there's not any wasted space. Oh, wait, I've only got 3 things stored in here, but actually, there was the possibility I might have had to store 1,000,000 things. So I could have a huge amount of overhead in memory overall. So this could be significant. Instead of just some, I'm just going to say yes. It's because of that pesky thing with using arrays where we have to brace ourselves for the worst case. We have to cover the possibility maybe in our application that there could be a million things in the array, even though in general, there's only going to be 7 or 8. That we've got a huge memory overhead problem, and you guessed it, this one goes to the linked list. 1, 2, 3, 4 versus 2. Arrays just aren't holding up terribly well, are they? Let me see, what else we got? Maybe we can, oh, here's one, sorting. Suppose we got to put this in order. Bubble sort or whatever sort you got. Almost all of those are described in terms of using an array. Let's put this array in order. So I'm going to claim that sorting over here is easy. Why? Because if we find 2 elements, oh no, my A and C are out of order. Temp equals A, C, copy that on top of the A, and then put the value of temp here. We're done. Over here, I don't have to tell you that once you start mixing and matching and moving around those pointer values, things can get pretty complicated in a hurry. And you better have drawn a picture, you're not even going to be able to get that to work. Bubble sort with a linked list is ridiculously hard. You've got to keep pointers to places that you've been, places that you're going, the current node. You've got to keep all that extra stuff because this is a one-way trip here. We don't have direct access. We're not going to be able to just exchange 2 nodes without any pain and suffering. That's going to be a pretty big deal. So the sorting over here, this is hard. And arrays are catching up. Good old arrays. Man, it'd be great if arrays just blew away linked lists, and we wouldn't have to look at linked lists at all. That's a tongue twister. Here's another one arrays have. Another perhaps easy, direct, easy one. Straightforward, easy. Let me see how many times I can say easy in the same sentence. Language support. What does that even mean? It means they're built in. You don't have to write classes to set up an array of strings or an array of integers. It's built into the language, and that's language support. C++ knows what an array is. C++ does not know, unless you tell it, which we're going to do. We're going to tell it. But C++ does not know what a linked list is. This is built by hand. This is standard transmission over here. This is automatic. So over here, the language support, I'll abbreviate. Language support, since I've already written it over there. No. Make that a question. Yes. Over here, no. And I don't know about you, but if they're going to give it to me for free, that's definitely an advantage over having to roll my own and make my own linked list class. So here we go with another guess. What have we got now? 1, 2, 3, 4. 1, 2, 3, 4. You know what? We'll declare victory and retreat. I'm going to claim this as a tie. We could come up with more advantages and disadvantages, but this is just to kind of give you an idea of the different considerations. What's the philosophical significance of this being a tie? It means they have both justified their reason to exist. There are some applications where a linked list is going to be much more appropriate. Specifically things like, well, there could be 1 million, I don't know, there could be 2 million. But in the average case, maybe there's 10 or 12. Yeah, a linked list, we might want to go that direction. An array, if we do know a lot about the data in advance, this is something about the senators of the United States of America. There would be exactly 100 elements in the array. We don't have to worry about dynamically allocating a new senator structure each time. It's going to simplify things if we just set up an array up front. So we don't always get to choose. That's the heartbreak of this. We don't always get to choose because as we study the application that we're trying to write an application for, the need for a linked list or the need for an array will reveal itself to us. We don't necessarily have to know everything about the problem up front, but as we study it, there's going to arise out of these two if we need what's called a linear container. A linear just means it's a straight line. What other kind of container could we possibly have? Well, we could have things like, they're not straight lines. They actually look like a spider web or something. There's graphs and stuff. That's something to look forward to in the data structures class, the CS3. I completely lost my train of thought here. Well, anyway, they're both linear containers, and this ABC business, don't let that throw you off. I know with CATS we had names, and with athletes, we had times and countries and all that sort of stuff. That changes per application. So what we're concentrating on now is just sort of the abstract arrangement of this. In other words, not ABCs. This could be 5, 12, and 13. This could be athlete structures in here. This is like a little freight train here, where each cargo car is connected to the one behind it, like a train. We don't even care what's in the cars. They're all sealed up and locked. We don't even look in there. If we are the ones responsible for making sure this thing behaves as a linked list, then that is on us. And I just now looked at the time. Good grief, it's 20 minutes. I'm going to declare this is the end of this one, and we'll go to video 2 for more deliberation and elaboration. I'm really going to have to be less wordy. See you online.